Welcome to part 3 of week 5 of the class Neuronal Dynamics. In the previous two parts of this week, we have seen that neuronal signals vary. Spike trains are not regular, the membrane potential fluctuates. And then the question arises, how can we measure, how can we describe these fluctuations? There are in fact different ways of doing this. A famous concept is the concept of rate coding. But that concept is not well defined. There are in fact three different definitions for firing rate. The first one is based on temporal averaging. And let me explain this one first. Suppose you look at an image and different neurons in various brain areas will respond to the presentation of this image. For example, neurons in visual cortex, neurons in memory-related areas, and these neurons are often organized in groups of neurons with similar properties. Suppose now that you record from one single neuron. At a given moment in time, you show the image is presented to the eyes, the information goes on to the brain, and the neurons respond. Now you record from a single neuron, and what you see is a sequence of spikes. And there are many spikes during the presentation of the stimulus. Now one thing you can do is you count the number of spikes. So in this case here, we would have 6 spikes in the period during the presentation of the stimulus. Then you divide by the duration of the stimulus. Suppose the stimulation time is 1 second. So I have 6 spikes in 1 second, or I have a firing rate of 6 Hertz. The rate in this case is a normalized spike count, normalized by the duration t of the measuring interval. In order to evaluate the rate, you just have to measure a single neuron for a single trial, but you have to average over time. Your measurement interval has to be sufficiently long. Now in this case, we have 9 spikes in our measure interval t. Now a different neuron may also have 9 spikes, but the spike train in this case is much more regular. In order to distinguish between the first case and the second one, it's important to look at the distribution of interspike intervals. In this case, there are some short intervals, there are some medium intervals, there are some long intervals. Whereas in the other case, all the intervals are nearly the same. So the interspike interval distribution measures the variability of the firing, or it's a measure of the regularity. This would be a regularly firing neuron, a regular firing spike train, and this would be a rather irregular spike train. An irregular spike train is characterized by a broad distribution of interspike intervals. The interspike interval distribution accounts for the regularity or irregularity of a spike train. Now let's come back to our measurement. So, we have presented a stimulus. In this trial, we found 5 spikes. Now we can wait a moment so that the brain gets back to its normal resting state and then present the same stimulus again. In the second trial, we would, for example, find 6 spikes. In the next trial, 3 spikes. And we do a total of, say, 200 trials, or K trials. In trial K, in the last trial, we would have 4 spikes. Now you see that the spike count measure itself is variable. It changes between one trial and the next. To see how much this variance is, one can calculate the Fano factor. First we determine the mean. So the mean spike count in this case would be 5. And then we look how much does each trial vary from the mean number. So some trials there are 6, some trials there are 4, there might be other trials with 9 or with 1. And this variance is normalized by the mean spike count. And this is called the Fano factor. Thus the Fano factor measures the repeatability across repetitions. So The spike count measure, firing rates defined by a spike count divided by a mean firing rate, are a very useful tool to analyze experimental data recorded in real neurons. However, there's a problem. The problem is that this is a slow way of coding. While this is a good measure to analyze experimental data, it's not a code that's used by the brain. It's not the code used by the neurons. And to see this, let me discuss a little example. Suppose I have a little frog sitting in its pond and it's waiting for the fly to come by. Now the fly passes close to the frog, and the total duration when it's in the neighborhood of the frog, it's less than 1 second. Now, if the frog used a spike count measure where a typical neuron fires at a few hertz, he would have to wait at least 1 second to count enough spikes. But after 1 second, the fly has already passed. So this is definitely not the code used by the neurons. So let's look at a different definition of firing rate. So let's again present our stimulus, say the Sydney Opera House, and we record in a first trial a certain number of spikes, and then we take a pause, we wait so that the brain comes back to the resting state, and we present the stimulus again, and we present it again and again. But now, instead of just counting the total number of spikes, we define short time windows. For example, in this first interval, we would count across all repetitions, we would find 1 spike. In the next time interval, we would find 1 spike. Then we find 3 spikes. Then we find 1 spike. Then we find 3 spikes again, and so forth. And so you can imagine that overall, this gives a time-dependent response. This is the PSTH, the peristimulus time histogram. Peristimulus time histogram. The histogram can start slightly before the stimulus. So we would have a few spikes before the stimulus starts. Peristimulus time histogram. Now, formally, this means we count the number of spikes in a short time window delta t across k repetitions. We divide by k. We divide by the duration of our counting interval. And then this gives a rate measure. It's 1 over time. Units are hertz. It's a rate measure, but now with a temporal resolution defined by delta t. For example, if you pick delta t equal 1 millisecond, you have a very nice temporal response pattern. Suppose the stimulus is presented here, then you see, for example, that at the beginning we have quite a few spikes, then we have a dip, then comes a second wave of spikes, and so forth. So now we have a temporal resolution of our definition of a firing rate. This is possible because we have averaged across trials. So this is a very powerful experimental tool. However, again, it cannot be the measure used by the fly. The reason is it's way too slow. Let's again consider our fly sitting here. And now the fly comes by. And the frog says to the fly, well, please fly again another 50 times so that I can average, so that I can finally catch you. So that's not going to happen. Fortunately, there is yet another definition of firing rates. I mentioned at the beginning that neurons are often organized in pools of neurons or populations of neurons with similar properties. Suppose we have a population of 500 neurons, and with a multi-electrode recording array, you are able to record from all 500 neurons simultaneously while you present the stimulus. So the picture is the same as before. The difference now is that this is a single trial And it's different neurons. The first line is neuron 1, the second line is neuron 2, the last line is neuron K. So in this case, the rate can be defined by a population average. I count in a short time interval delta t, I count all the spikes across the different neurons in the population, I divide by delta t, I divide by n, the number of neurons. There are n neurons, and because I divide by delta t, it has again units of rate. The units are 1/time, the units are hertz. Now I would claim that this is a rather natural situation for neurons. Consider a postsynaptic neuron. A postsynaptic neuron receives hundreds of inputs from other neurons. Suppose some of the inputs come from the same population of 500 neurons. So effectively, this neuron would be driven by the population activity, by the population of spikes arriving in each short time interval delta t. So in that sense, this definition of a firing rate defined as a population average, is natural. So let me summarize. There are at least 3 different definitions of a firing rate. All 3 are useful experimental tools for data analysis. The first one is based on temporal averaging. Temporal averaging cannot be the code used by neurons because it's too slow. The second one is repetition across different trials and then averaging. Again, in a natural situation, an animal is not going to average over different trials before it can react. And the final definition is that of a population average. Let's assume that there are groups of neurons with similar properties. Then we can define a population activity, a firing rate averaged across the population. So the repetition experiment measuring a single neuron and then averaging over k repetitions of the same experiment can be seen as an approximation of the population coding used by the brain. Before we continue, please have a look at the quiz.